Hi there. Oh, Hi there. This video is going to walk through an introduction to orbital energy levels for different types of atoms and electron configurations. All right, so now that you're familiar with the different types of orbitals that your electrons can occupy, okay, remember your different energy levels N, 1, 2, 3. So as we go higher in energy, okay, we get different types of orbitals available to us. Okay, we get our S and our p orbitals, d orbitals. If we go even higher in energy, we would start to see some f orbitals come into play. Okay, so these types of diagrams that you'll see are what we call energy level orbital diagrams that represent the relative energies of each individual orbital. Okay, so for hydrogen-like atoms, okay, when I say hydrogen-like atom, what I mean is a one electron system. Okay, so any atom that has just one electron is going to have an energy level diagram for its orbitals that looks like this. Okay, so what's distinct about this energy diagram is that all of the subshells, okay, your S subshell, your P subshells, okay, for a given energy level are all of the same energy, okay? They're all on the same horizontal line, which means that they are what we call degenerate orbitals or equal energy orbitals, okay? So degenerate means equal energy or same energy. Okay, so if we go up to our n equals 3, all of the subshells corresponding to n equals 3 we see are on the same level. So these are all degenerate orbitals. They all have the same energy. Okay, and again, this is a hallmark of our one electron systems. So as you put electrons into these orbitals, again, you're only dealing with one electron, okay? So you start off with your lowest energy. You can put a little electron in there, spin up or spin down if you wanted to, okay? You would be able to excite that electron up into these different orbitals, okay, that all have different energy levels, okay? So you could go into 2s or 2p, those would all be the same kind of delta E calculation, okay? Similarly, if you jump up to the n equals 3 orbitals, okay? All going to be the same delta E here. If we look at atoms with more than one electron, you can see things get real fun, okay? So once we have more than one electron in there, we have essentially electron-electron repulsion to take into account, and that changes the relative energies of these subshells. Okay, so you'll see here that our n equals 2 subshells are not degenerate anymore, like they were for our one electron situation. Okay, same for when we look at n equals 3. Okay, so our 3s and our 3p orbitals we see are at different energies. Okay, those energy levels we say start to split, to separate from one another. And you'll start to see even that we get some interesting ordering of our orbitals. So we go from 3s to 3p to 4s, back to 3d, to 4p, up to 5s, back down to 4d. So there's not really an intuitive ordering if you look at how this energy level diagram is put together. Okay, so what we have at our disposal is this handy tool for remembering the relative energies of orbitals. Okay, so this essentially helps you to figure out what order are these lines, am I going to draw these lines at? What order am I going to be filling my electrons from low energy to high? Okay, so how this little tool is put together is you just write your orbitals of a given energy level, all the energy levels on the same, the n levels on the same line. So n equals 1, n equals 2 options, n equals 3 options, n equals 4 options, so on and so forth. Okay, so every n value stays on one horizontal line. Okay? These arrows that you see drawn, essentially when you draw the diagonal arrows through, as you see, and you follow those arrows through from tip to tail, okay, that gives you the ordering that you're going to be filling your electrons, okay? So if you look at this ordering, we go 1s, 2s, 2p, 3s, 3p, 4s, we should see that same ordering if we follow our arrow. So 1s, 2s, 2p, 3s, 3p, 4s, and so on. And you'll see that it mimics the ordering that you see as you go up this energy line. Okay, so if you are ever in a position where you have to create one of those energy level diagrams for your orbitals, just pull out this tool if you can't remember how to draw it, and that will tell you the order that you want to draw your orbitals. Okay, so now that we have all of these options for places to put our electrons in an atom, we need to have a way to describe where the electrons are in these orbitals. And the tool that we use to do that is something called the electron configuration. Okay, and it tells us how electrons are distributed among the various atomic orbitals. Okay, so this is the standard form of an electron configuration. Okay, the number out front corresponds to our principal quantum number n. Okay, we've done a lot of work with that one. Okay, the letter that comes after represents your angular momentum quantum number L. So remember that L has a letter that's associated with it as well as a number. Okay, so for this s orbital, remember L equals 0 corresponds to the letter S. Okay, so don't forget those letter designations for your different L values. The last part of your electron configuration notation is this superscript that comes after the orbital label, or your angular momentum label, I should say, which is representing the number of electrons in that orbital or subshell. Okay, so this is where you have to remember how many different types of each orbital you can have. Okay, so remember you get one s orbital, 3p orbitals, 5d orbitals, or 7 f orbitals, okay, total for each energy level. That's going to dictate how many electrons you can have in each orbital. Okay, so you can have two electrons for each s orbital, a total of 6 electrons for your 3p orbitals. You can have 10 electrons total because you have 5d orbitals, okay, and then 14 electrons in your 7 f orbitals. Okay, so remember you can find the total number of orbitals is based on your total number of m sub l values that are possible. Okay, so don't forget your quantum number rules. That's where you have 1s, 3p, 5d, and 7f orbitals. And each one can hold 2 electrons, so we get 2, 6, 10, and 14 as our total. So you should never have more than 2 in that superscript corresponding to an s orbital, never more than 6 corresponding to a p designation, never more than 10 as an exponent corresponding to a d orbital, and never more than 14 corresponding to an f orbital. So we can put together our electron configurations in a really easy way using our periodic table. So the only thing you have to really remember here is that each section of your periodic table fills a different type of orbital as you add electrons. Okay, so for right now, just keep in mind that your first 2 columns, your first 2 segments on the left-hand side fill the s orbitals. If we go over to the right-hand side, okay, those elements are going to fill your p orbitals. Those electrons will fill your p orbitals. Your what we call our d block, our transition metals, okay, here in the middle. These fill your d orbitals. And these two rows that usually hang out at the bottom of your periodic table, they're the ones that are tucked in between here. You'll notice you'll get atomic number jumps right in here somewhere. Okay, all of these elements are tucked in there. Okay, these fill your f orbitals. Okay, so the way that we kind of verbally refer to that, we would say s block, p block, d block, or f block elements. Okay, so again, just some vocabulary that you'll hear thrown around a little bit. Another way that we can represent our electrons in our orbitals is using something called a orbital diagram. Okay, these are going to come in real handy when we start to try to predict reactivity and trends in our atoms. So all this is representing here is you have a box, or if you're lazy like me, I just draw the horizontal line at the bottom to represent an orbital. So each orbital gets a box or a line to represent it. Here we have a 1s orbital. So we have one box to represent that s orbital. And for hydrogen, we know that we have one electron in there. Okay, so we put an arrow in there to represent our hydrogen. If I wanted to draw a similar situation for our next atom, so for helium, draw another box. We're still filling the 1s orbital because we've got room for one more electron in here, right? So we have a spin up electron. We've got room for one more spin down electron. So that helium, that extra helium electron, we'll put in as a spin down. Okay, so now that s orbital is all full, we're going to have to move on to our next highest energy orbital. Okay, so again, looking at our chart here, so we just filled the 1s orbital. Next up, we would start filling the 2s orbital. Okay, so I hope this video was helpful in getting you familiar with the notation we use for electron configurations and our orbital diagrams. And we'll have another video where you will get to do some practice using these new tools. Thanks.